Stevens, and I lead controls and automated systems in RNA. I am really honored to introduce our special guest today. For those of you that work in anything to do with automated driving, you'll know that Mobileye is one of the most respected names in the industry. They cover a huge range of technology, from the most basic driver assistance features all the way through surround vision and all the way through to level 4 robotaxis. And so today we are really honored to have Shai Shalev-Shwartz with us. He is going to give us a talk on lean driving policy. It's going to talk through the design principles underlying how Mobileye does driving policy. So driving policy is what allows the vehicle to both make good progress and provide a naturalistic driving experience, and to do it safely. And this has to be done super efficiently because it all has to be done in real time. And so this is going to be an excellent talk. Shai is a senior fellow at Intel and chief technology officer of Mobileye, which is an Intel company. And I think those who are following the news are interested to see today that Intel intends to take Mobileye public next year. So Shai, congratulations on that. He leads the software and algorithm technology development for Mobileye's advanced driving assist systems, ADAS, or what we call DAT, highly autonomous and fully autonomous driving solutions, and all the enabling technologies that go with that, including responsible sensitive safety, RSS, and road experience management maps. He's also a professor at Rachel and Celine Benim's School of Computer Science and Engineering at the Hebrew University of Jerusalem. Shai developed the science behind RSS, as well as an economically viable path towards a future where there are no casualties from car accidents. He is drawn to autonomous driving at the first large-scale deployment of artificial intelligence and machine learning outside of the cybernetic world. He's best known for his pioneering research in machine learning, and was actually listed as one of the 100 most influential researchers worldwide in 2016 by A-Minor. In 2014, he co-authored one of the top books used by major universities on theoretical machine learning. It's called Understanding Machine Learning from Theory to Algorithms. Before joining University of Mobileye, he was a research assistant at Toyota Technological Institute in Chicago, and also worked in research at both Google and IBM. He's written more than 100 research papers focused on machine learning, online prediction, optimization techniques, and practical algorithms. In 2020, he was awarded the prestigious Michael Bruno Award for his groundbreaking research and his unique contribution to computer science and engineering. And maybe just one final comment from me. I first went in a Mobileye highly automated vehicle in Jerusalem back at the beginning of 2019, and it remains one of the benchmarks for any automated driving vehicle I've been in the way that it was able to drive through and negotiate some pretty dense and aggressive traffic. So I'm super excited to introduce Shai. Thank you so much for spending time with us, and I'm looking forward to your talk.
Thank you very much. So I'm going to talk about lean driving policy. The focus will be on the methodologies and design principle for our driving policy in Mobileye. The system that I will describe today, we call it a Supervision System. It's a camera-only system. There are 7 cameras plus 4 parking cameras, and all of the compute is on 2 IQ5 high. Each one takes only 10 watt of energy, so very lean system. Basically what the system is doing, so we feed the 11 cameras as well as the road book, which is our REM maps, and also a driver monitoring system. All of this goes into the 2 IQ5 board. It performs full surround vision, understanding everything around us, localization on the map, the driving policy with the safety math model of RSS. All of this goes back to the control of the car, and this system is already actually in production. The first 2,000 vehicles were already delivered to customers in China. Zeekr is a model of the big company Geely. So let me show you a little bit how the system works. So here is a system, cameras only, 2 IQ5 chip, driving in Jerusalem, doing a roundabout, another car in Munich, there is an emergency vehicle, the car waits, try to see what to do, and then figures out it needs to move on. Detroit, unprotected left turn. New York, our car drives in New York, where there is plenty of pedestrians and all sort of crazy things. I think it's also raining in this video. Lately we started to work also in Paris. So this is a video in Paris. You see the mess that is going on here. Some taxi driver cut, and we need to merge into the Champs-Élysées. This shows all what you saw here is a supervision system, 11 cameras and 2 IQ5 chips. So what is the spec of an IQ5? The CPU is a MIPS with 64 bits, 8 cores, 16 threads, running at 1.5 gigahertz clock speed. It has accelerators, propriety of Mobileye, that performs deep learning operation, 16 TOPS, and the power is 10 watt. And we have 2 such IQs on the supervision system. So the focus of this talk is about the driving policy part. So usually in robotic methodology, we follow the sense, plan, act methodology. Sensing is understanding where we are, planning is deciding what to do next, and acting is moving the throttle and brake and steering wheel in order to fulfill the plan of the driving policy. This talk again is about the driving policy part. What the driving policy is doing is the decision making, and it's a type of reasoning of what would happen if. So the car needs to plan ahead and figure out what to do and what would happen if it will do something or something else. Okay, so a little bit more to the details. Driving policy is a mapping from sensing state, which is our description of the world around us. It contains the road, our location on the road, static obstacles, lane semantics like solid line, dash line, traffic lights, kinematic state of other road users like pedestrians and cars, occlusions handling, etc. This is a sensing state. And then driving policy needs to look at the present sensing state and figure out what is a desired action, what to do next. And the desired action is simply speed and curvature commands for the car. Why driving policy is difficult? So unlike the sensing part, there is no ground truth. In sensing, when you need to figure out if there is a vehicle in some place around you, you can construct ground truth. Either there is a vehicle there, or there is no vehicle there, and you can set the ground truth. In driving policy, there is no right choice, okay? So you can decide to accelerate or to brake a little bit. Both of them can be totally fine. So you don't have a clear definition of what is right to do at any given moment. In addition, actions that are performed now may have long-term effect on the future. So action that seems to look perfectly fine now may have consequences in the far future. Moreover, it's a closed-loop system because actions of the ego vehicle affect other road users. For example, when you perform a lane change, if you are pushed a little bit, you will affect the behavior of the cars on the other lane, and they will react to you. So it's not something that you can say, okay, I know what all others will do. It depends on what you will do. So it's a game. Finally, you must handle uncertainties about the future. The uncertainties are both about what others might do, as well as there are areas in which you simply don't see what happens. So you need to figure out how to react to what you don't know. And really the focus of this talk is about the computational challenge of driving policy. So as I showed you, the supervision system have two IQ5 chips, and the driving policy part running only on the CPU. So it's basically have not a very strong server of CPU, but only an okay CPU, and we need to do all the planning on the CPU. And the question is how to do it efficiently. And the challenge is that actions that are performed now may have long-term effect on the future. So we must plan for a sufficiently long time. As you can see in this image, suppose the ego vehicle is a red car. It drives at 10 meters per second. If it plans only for the coming 2 seconds, meaning 20 meters ahead, it doesn't even know or see the yellow car ahead. So the plan in white looks perfectly fine. Of course, it's not a good plan because 2 seconds ahead is not enough. We must plan for much more. But once you plan for a very long time, the uncertainty about what other agents will do, and moreover how they will react to your actions, becomes harder and harder. So what you will see here, this is a current state. Suppose the ego vehicle is a red car, and there are two other cars, two white cars. The front one is very slow, so the rear one wants to overtake it. But how it will overtake it depends on our action. So I will play a video here. It's a two images. The top one is one possible behavior of the agent, and the bottom is another one. And in the top one, the other agent yields to the ego vehicle, while in the bottom one, it takes the right of way. And the reason is because what the red car did. So if the red gives a signal that it's going to let the other car merge in the lane, then it will react in one way, and otherwise it will react in another way. So once we plan ahead for a long future, there is a lot of uncertainty about what other agents will do, and moreover, they will react to our actions. Now, this is not just a theoretical thing, it happens on the road all the time. So here is an example where there is a slow truck ahead, there is a car after the slow truck that is stuck after the slow car. The AV, our system, arrives, and since it plans for a sufficiently long time, it can know in advance to change lanes and to slow down sufficiently, and other agents respond to our behavior. So let me play this video. So there is a truck far ahead. You can see that we decide to change lanes. We need to slow down in order to go after the car in the next lane. And then we see indeed that there is a slow truck on the right, and we can overtake it. Now, if we wouldn't plan in advance, then we will not be able to see the slow truck or to react properly to the slow truck. I will show it again, and you will see. Just a second. Let me play it again. Okay, so there is another driver behind the slow truck, which is stuck because it didn't plan in advance to make the change lane, and then it is in a difficult situation that he is trying to change lanes while there is a fast fast traffic on the other lane. All right. So how do we tackle driving policy? Let's first look at the existing approaches for driving policy, and roughly you can think about three methods. I list here four because the first one is not really something that you can really do. It's a brute force search. It's not practical in any way. But what people are actually doing is either some search method, approximate search method, for example, Monte Carlo tree search, MCTS. Another family of methods are dynamic programming methods, either on Markov decision process or linear quadratic regulator, but assuming some simple model of the future behavior, you can solve the planning problem using dynamic programming. And the other family of problems is learning-based problem, where you do end-to-end learning, either by imitation learning or by reinforcement learning. So let's go into more details. The brute force search is here mainly for pedagogical reasons. It's not something practical. What does it mean? You search over the entire future of action sequences, not only for the ego vehicle, but also for all other agents. Then you evaluate every sequence, and now you pick the current action that leads to the best future. Of course, there is a definition of what is a best future, but this is not a very difficult decision to do. So this is how you find the action for now. The pro of this, the advantage of this method is that it can guarantee optimality, but of course the disadvantage is that it's not feasible due to the exponential size of the search space. So this is not something that we can actually do. So let's go on to methods that we can actually do. The second method is Monte Carlo tree search. The idea is like the brute force search, but instead of searching the entire space, we search only a small part of the space by simulating many possible futures while using a deep neural network to guide the search. This is an approach, for example, that was taken by AlphaGo. And then using some model for the other agents, because we simulate not only our behavior, but the behavior of all other players as well. The advantage of this approach is it considers the response of all agents to our actions. So it's really a game. I will do something, the other agents will respond, I will next do something, and the other agents will respond as well. We really simulate the future. The disadvantages are first that we need a model to use for other agents, and if we choose some models, there may be a mismatch between the models that we are using in the simulation versus reality. So this mismatch can shift our search space and our understanding of what is going to happen, and we might plan wrongly about the true future. The second disadvantage is that the search is not complete. We only use some rollouts of the future and not the entire space. So either we use only few rollouts, but then we pay for suboptimality of the search, or we apply many rollouts, but then we require too much computation for a real-time system. So there is an inherent trade-off between the optimality of the search and the runtime it will take for a real-time system. And while Monte Carlo tree search has been used successfully for games like chess and Go, if you're losing in a driving game like we are talking here, then you might get killed. If you're losing in chess, it's not that bad. Okay, so the next family of existing approaches is dynamic programming. In dynamic programming, you start by making the word simple. What is a simple word? For example, Markov decision process. A Markov decision process is a word in which all the future depends on the current state of the word. You couple all the word into the state. And you don't need to look backward more than one state. But we know that in driving, the next thing that is going to happen in the world is not following the Markovian assumptions, because it depends on the other agents. We don't model the other agents in our state. So in order to make the future behaves like a Markov decision process, we predict a single behavior for each of the other agent. Once we predicted its behavior, we can model the future as a Markov decision process. And then we can calculate an optimal planning using dynamic programming like the value iteration algorithm, which is based on Bell-1 equation, or any other approach. So the advantage of dynamic programming is that you can guarantee optimality of the search with respect to the predictions if the state space is small enough. But the disadvantages are, first, there is a technical issue of chaos of dimensionality due to the requirement to discretize space and time, and this might yield, again, an expensive calculation. You can overcome it in some methods. This is not the main point. The main point is that there are no guarantees about your search, simply because you just imagine one possible future and do not take into account the real uncertainty about the future behavior of other agents. So what we are doing here is that we commit to a single or even few future behavior per agent, and this future behavior is independent of what the ego vehicle is doing. Now, this makes our world simple. It is a Markov decision process, and then we can plan very efficiently, but it's not the real world. The real world is most likely not going to be according to our prediction of the other agents. It might change, and therefore all our guarantees about the search are not relevant to the real world, and overall this approach is not safe. Moreover, if you there is a principle which I call it the Vapniks Principle. Vapnik is one of the founders of the academic field of machine learning and theoretical machine learning, and he has a principle of how to learn. And the idea is that when you solve a given problem, it is better to try to avoid solving an even harder problem as an intermediate step. Now, both Monte Carlo tree search algorithm and dynamic programming violates Vapniks Principle, because you shift the problem into one of building a model for the behavior of other agents or predicting what they will do. And this is a very difficult problem, figuring out how humans are behaving. It is much harder to figure out how exactly humans are behaving than reacting to their behavior. Okay. The last existing approach for driving policy is what we call end-to-end learning. For example, you can perform end-to-end imitation learning, where you imitate a human using some deep networks, and this goes back to 1989, where a driving reflex was developed and showed to behave pretty good, or more modern reinforcement learning algorithms, for example, end-to-end policy gradient using some deep policy function. So end-to-end learning has the advantage that the approaches don't rely on explicit predictions of other agents. We just learn this is a state, how to behave. We don't explicitly predicting how other agents will behave. And they are also computationally efficient because we don't need to roll out the future. The disadvantages are, first, that there are no guarantees. The quality of your driving policy relies on how good you succeeded in learning a policy. And in practice, there are no impressive empirical success of the end-to-end learning approach. Moreover, from the engineering point of view, it is very difficult. So even if you manage to make some end-to-end method work well in some specific cases, but then you find a problem, it is very difficult to fix it. Unlike in supervised learning problems where validation and retraining is a well understood and easy to do a very clear methodology, because it can be done in an open loop manner. Here in policy, if you see a problem and you change your deep networks and now the ego behavior is changed, then the other agents will react to this change, and then either we rely on a simulator and then we might suffer from simulation versus reality mismatch, or we recreate a scene in an open loop manner while only changing the ego behavior, but then again you suffer from simulation versus reality mismatch because the simulation is not truthful to reality. And actually, a personal story, when I started to work on driving policy, I applied many reinforcement learning methods, and they were really good most of the time. Then I let a simulation run overnight for the same scene, say 100,000 times, and there was one accident. And now you say, okay, it's pretty good. One accident in 100,000 experiments. You fix something, you change a little bit, you do some boosting, you change the reward, you shape the reward, you do all the tricks of machine learning, and then you let it run again in the night after that, and then you come in the morning again, and again, it works very good, but there is one accident in 100,000 simulation. And then you fix again, and the later morning you again find another accident of another type. And there is a heavy tail of edge cases that it is very difficult to control it. As an intermediate summary, we discussed the MTCS, Monte Carlo research, dynamic programming, end-to-end learning, and to the best of my understanding, all the players in the academy or the industry relies on variants of one of those approaches. Hence, they suffer either from lack of guarantees and or from heavy computation load. So now comes our approach and our methodology. So our methodology is to assume the worst case under a well-defined set of reasonable assumptions, and then couple all the future into the present using analytical calculations. Okay, so I'm a little bit taking the hat of a computer scientist. In computer science, we always love to analyze the worst case. What's the worst case complexity of something? What's the worst case performance of something? Now, taking the worst case without any assumptions might lead to something which is not useful. But then you can have a well-defined set of reasonable assumptions about the future, and beyond them you don't want to assume anything and you want to take the worst case. Now, the advantage of this is that unlike dynamic programming methods, which also requires predictions, our method does not need predictions. The reason is that we analytically couple all possible reasonable futures into the present. So dynamic programming and these approaches of value iteration and dynamic programming based on Bellman's equations, the heart of the approach is to couple all the future into one quantity, like the value function or the so-called Q function, and then you have a very lean computation because you coupled all the future into a property of the current state. We do the same, but we do not plan for a specific prediction. We couple all the possible reasonable futures in which the ego vehicle will do something, other agents will react, the ego will do something again, other will react. All of this infinite set of possible futures, and we manage to couple all of them into the present. Now, this is one important part of our methodology. The other part of our methodology, in order to have comfort driving, we construct intentions. Intentions of other agent. Intention can be a car is giving the right of way or taking the right of way, or a car is performing a U-turn now, or is pulling over from parking, or a pedestrian intends to cross the road or not. It's not prediction, okay? It's intention. I don't know exactly how a car is going to perform a U-turn. I'm just saying that it intends to do a U-turn. Same about giving way or taking way. A car is yielding to me. I don't know exactly how it's going to do this, but it's going to yield to me or take the right of way. And those intentions control parameters of the reasonable assumptions, but they have no effect on the safety. They have only effect on the comfort of the ride. Using intention rather than predictions yields a human-like behavior. And we do use deep learning in order to construct those intentions, but we can construct them in an open loop manner because it's not something that is very, very specific about how exactly someone is going to perform some maneuver. Now, this methodology of worst case under reasonable assumptions is actually what governs our safety model of RSS, Responsibility Sensitive Safety Model. So the same methodology gives us a safety net to our decision making, and not only to our decision making. You can take any method and apply RSS on top of it in order to get a safety net to the decision making. But the focus on this talk is not about the safety, but instead how the RSS methodology also yields lean computation, also helps us to have a very capable driving policy under a very lean computing platform. So unlike the vanilla RSS model, we devise a more complicated, still computationally efficient, we call it comfort RSS model, in which we employ comfort kinematic measures. For example, we take into account the jerk and not only the acceleration. And the coupling of future to the present is continuous rather than just safe, non-safe. We have measures similar to what being done in Markov decision processes, where you have the Q function, value function. It's a continuous function that approximates the behavior on all the future. Here again, in comfort RSS, we have such measures. So let me give you few slides about the essence of the comfort RSS method. I will start with a short one-slide reminder of what is the RSS model. So the RSS is a formal model. We published it in a white paper. The model is for safety, and it provides mathematical formalization for the AV to never cause an accident. So you can think about it as a safety net layer for any decision making. The idea is to define reasonable boundaries on the behavior of other road users. Within the boundaries, you always assume the worst case behavior of other agents. And the boundaries capture the common sense of reasonable assumption that human drivers make on other drivers. Any action beyond the defined boundaries is not reasonable to assume. And the model manages to couple all the future into a single number of safe, actually a Boolean of safe or not safe. Now, let's look at the RSS model in the simplest scenario possible of a car that follows another car. So we have here the black car and the ego car behind it. In the vanilla RSS model, the reasonable assumption is that the front car won't brake stronger than some parameter minus A max. The parameters of the rear driver is its response time and the maximal brake it can apply. Then a proper response for the rear car is simply to apply the maximal braking after response time. And these definitions allow us to say that a state is safe if rear will apply proper response and front adheres to the reasonable assumption, then there won't be a collision. So this means that our current state is safe. And then the RSS is very simple. It tells you that if the rear does whatever it wants, but at the first time in which the state becomes non-safe, it performs the proper response, then you are guaranteed to have no collisions. So we couple infinite possible futures. We don't know exactly how the front car is going to drive or how the rear car is going to drive, but we couple everything to one boolean, safe or not safe, and we have guarantees that if you apply proper response at the moment in which the situation becomes non-safe, then there will be no collision. And you can look in the paper about how we prove this property, how we couple all the future into this statement using inductive arguments. Now, a generalization of the RSS concept is to change a little bit those definitions. So the reasonable assumption on the front car is arbitrary constraints on the braking profile of the front car. The proper response for rear car is arbitrary kinematic response policy. And then we can define again, based on the reasonable assumption and the proper response, what is a safe state. If the rear will apply its proper response and front adheres to its braking profile, then there won't be a collision. And again, we can give guarantees that if we are currently at a safe state and that the first time in which the state is not safe, then the rear car performs proper response, then there will be no collisions. Okay, so it's basically the same, but we are talking in a much more general approach. And now we can talk about comfort RSS, which is not a safety thing, but a comfort thing. So one simple example, the reasonable assumption on the front car again will be that it won't brake stronger than minus A max, but note that this parameter should not be a parameter of really, in terms of safety, maybe we need to assume that A max is 6 meter per second square or 10 meter per second square, 1 G or half a G. Here we can even define a comfort RSS in terms of 0.2 G or 0.4 G or 0.7 G, and we can have several such assumptions. For each we can define a proper response for rear car, and what we're doing is a bounded jerk braking. So you want a comfort brake, so you bound the jerk. And again, you can define a safe state in the same manner. If the rear will apply its proper response and front adheres to its braking profile, then there won't be a collision. And you can give guarantees that if you start from a safe state and apply the proper response at the first time in which the situation is not safe, then there will be no collisions. Now, the nice thing is that if you choose the reasonable assumptions and the proper response smartly enough, then you can calculate analytically if the situation is safe or not safe. And you can see an example of this in another white paper that we published about an ADAS platform for comfort RSS. So let's combine all of the components together. We consider, for example, a merge situation like here. So the white and red cars are going to merge. The important thing for the white car to figure out is whether the red car intends to give way or not, to give the right of way or not. Given that it intends to give the right of way, the exact prediction of how is not important. And same wise for the red car. If it yields to the white car, it should prepare for a worst case braking of the white car. and under the reasonable assumption that it puts on the white car. And then from this moment and on, everything becomes analytical calculations. So in such a scenario, you can decide all the time if the other agents, what are their intentions. For example, by deep learning, and we apply such deep learning methods for figuring out possible intentions of other agents. And then we calculate the worst case under those intentions for all agents analytically. And by this we get a very, very efficient way of figuring out what to do with respect to all of the other agents. So here is an example of the same logic. This time it's not a structured road with a clear yield, with a clear merge logic, but instead it's a very, very narrow street. And you can see the ego car, it has a Mobileye sign. We pictured it from a drone, and we are here in a narrow passage. Some car coming very, very fast, the other one slows down. We figure the intention, and from there on, everything becomes analytical calculations of how to respond. The scene is very, very dense. Doing predictions for all other agents is very, very difficult. Here is a unprotected left turn. There is a big bus that's coming, and there is occlusions. Nevertheless, the calculations are all very, very efficient. A pedestrian comes and goes. The other car almost hits a pedestrian. We are negotiating with the other cars. Everything is very, very natural. We just try to figure out the intentions of other cars and fastly compute worst case scenarios given the intentions and continue. The same is applied for pedestrians. So here is again a very, very narrow street. There are two pedestrians in the bottom in the image. You can see that they are talking to each other. The car figures out that they are not intend to cross the road, and it continue to drive. And this is how even in dense scenarios you can have a very efficient computation. So to wrap up, I outlined several approaches, existing approaches for driving policy, and I discussed guarantees, efficiency, and what the methods requirements on other agents. So the brute force approach is guaranteed to work, does not require anything on other agents, but it's not practical at all, it's not efficient. Monte Carlo research has no guarantees, both because you use a model on the other agents and because you are doing an approximate search and you are doing only few rollouts of the future. So you do not have guarantees. In terms of efficiency, it depends on the number of rollouts, so the efficiency is linear with respect to the number of rollouts that you are making, and you get a trade-off between efficiency and the quality of your policy. Dynamic programming, you require predictions for other agents, which is a very complicated task. You get efficiency because you can couple all the future into the present, but you have no guarantees because your model does not reflect reality, and in particular it doesn't take into account the fact that other agents will respond to your actions. The end-to-end method has no guarantees, like learning methods, and has many engineering difficulties, but it is a very efficient method, and it does not require anything on other agents. Our method has guarantees because of the RSS guarantees, so we can state very, very clearly what are the assumptions that we make, and we can give crisp guarantees on our driving policy based on the assumption that we make on other agents. The method is very efficient and runs on a lean computing platform that goes in production nowadays. The requirements on other agents is intentions, and we perform those intentions using deep learning methods as well as other approaches. So in a sense, we get the benefits of all worlds because we have clear and crisp guarantees, we have an efficient method, and we do enjoy the benefits of deep learning, of modern deep learning methods, by giving human-like understanding of our actions based on explicit intentions classifiers of other agents in the scene. I think this is a good time to end, and I would be happy to take questions. Thank you.
That was outstanding. Thanks so much. So to those online, if you would like to ask a question, please post it in the chat. Maybe I'll kick the questioning off here. At the beginning, you showed the video of Paris, and anybody who's driven in Paris has to respect anybody, human or automated vehicle, that can drive in Paris. And then you also showed that unprotected left, which again, I think many humans would struggle to do as well as the car did. Can you maybe talk a little bit about what is the role of simulation in improving out and analyzing perhaps some of these really hard cases which are different every time you arrive?
Yeah, so I want to first distinguish between a simulation for the sake of validating your driving policy and simulation for the sake of constructing rare cases for your perception system, for the sensing. So let me just bring this slide of a sense, plan, act. So in the sensing, most of the sensing, since it's open loop, depends on learning methods, and especially deep learning, because this works the best. But other methods as well, and you might have many rare cases, and their simulation can help you a lot. For example, an animal that crosses the road is something pretty rare. If you can create simulation of many different types of animals or different type of weird looking cars or other things, then you can improve your sensing, your perception system. There is the other thing is for the driving policy. So what we're doing in driving policy, we use simulation for validating our system in terms of making sure that we don't have bugs, and making sure that that we react comfortably enough to many situations. But the nice thing about the methodology that we are using is that you can give crisp guarantees without using any simulation. Okay, some of them are public, like the RSS, but some of them are internal. It's not something that we publish out, but we have clear guarantees also on comfort, because we make explicit the assumption that we make also in our comfort function. And since we are equipped with the mathematics behind RSS, we know that we just need to validate that our assumptions are sane, and we can validate it open loop, okay, in an open loop manner, because if we make some assumption that something is very, very rare, we can check it out in an open loop manner. Once we validate that something is very rare, and we validated that a certain response is comfort enough, and all of these should be defined, right? But once you validated this, you have mathematical guarantees that under the assumptions you always will be comfort according to your definition. So simulation helps us in development and finding software bugs and evaluating efficiency of computation and improving efficiency of computation, and also thinking about how things are look like, and also training intentions. In all of these cases, simulation helps a lot, and it's a valid tool, and we use it a lot. But on top of it, we also have the mathematical guarantees, which are much stronger than the simulation tool.
Thank you very much. Not seeing any questions in the chat yet, so I'll keep on going. This idea of intention, I think it is...
Sorry, Craig, there are a few questions in the chat. Maybe press the chat window.
I am not seeing them in the chat window. Michael, maybe you could please go ahead.
There's a question from Eric Tang. I'll just read it out loud. Thanks for the insightful perspective about reasonable assumptions regarding other road users and agents for safety guarantee. However, although sensing and perception can be a learned open loop without the interactive challenges, sensing and perception still have a heavy tail distribution given the wide variety of road environment and driving cultures. So the question is, with this understanding, how can you guarantee safety in the presence of sensing and perception long-tail uncertainties or worst case? That was a long question.
Yeah, that's a great question. So the answer is that we use combination of things. First, a straight vanilla statistical methods. If you want to guarantee, if you collect random, say m hours of driving, okay, from the distribution of driving that you are interested in, and you have ground truth for your sensing system on these hours, then you can guarantee using classical statistical methods that the probability that you will make an error is roughly 1 over the number of hours you collected, if you don't have any errors in these hours. This is one layer. It's not sufficient in my view, but it's one important layer. The second layer is that for level 4 type of systems, we rely on what we call true redundancy. So we are building 2 systems. Each one of them can drive the car fully. One of the system is a supervision system, which you saw. It is based on cameras alone, no radars, no lidars. The other system is based only on lidars, radars, and only one camera for traffic lights. But all the functions except traffic lights are solely based on a lidar and radar sensors. And we developed both of them, and we can drive autonomously for hours on both of them. Now suppose that you validated both of them independently. If they are independent, then the probability that both of them will fail is a product of the probability that each one of them will fail. Of course, there is an assumption here that they are independent, which is not perfectly valid, but this is a methodology that is being used all over in the industry for heavy tails. So for example, when you build an airplane, you build redundancy, you build several systems that perform the same thing, so that if one of them will fail, the other one will save you. Sometimes the systems are not independent. You put 2 engines on an airplane. Hopefully, if one of them will fail, the other will not fail. Although these systems are not independent at all, they are dependent, and they have common failure modes. But still, it gives you a lot of benefit. So this is the second layer. The second layer is that we believe that for L4 systems, building 2 independent systems is something very, very useful and will increase the levels of safety a lot. The third thing that we are doing is that we are building algorithms that for the safety layers are agnostic to the heavy tail of what you might expect. And let me explain what I mean. You are driving on a road, okay? You need to, you are building using machine learning a car detection system. Now comes a very strange car. Someone put a boat on a car, or I don't know, someone painted its car in a very strange way, or whatever. It might be the case that your classifiers that were trained on other data will fail on this car. But now consider another algorithm. Consider an algorithm that does not detect cars at all. It detects the road, okay? And so it detects where is a road and where is something that is pixels which are not road, okay? This classifier does not know the difference between a pedestrian and a car and a barrel and a fence and a sky. It just knows that all of these are not road, okay? It is much more robust to a very strange looking car, okay? So if you build correctly the composition of the classifiers that you are making, then you get a very, very high level of redundancy. And this is a very important methodology that we are doing in Mobileye. We never train a single system. We don't believe in an end-to-end neural network that performs anything. There are other companies that rely just on big data, and they have, a big neural network, and with more and more data, they hope that it will solve all the problems of the world. We believe that one must build many, many different ways to understand the same thing. So the radar lidar system versus camera system is just an extreme example, but even in the computer vision part, we don't have a single method that detects car. We have many, many different algorithms that detects cars, and that detects what is not a road, and that detects occlusions, and that detects many, many other things like that. And only when you combine many, many different ideas, you are more robust to the heavy tail. Last, we do use simulation in order to construct things which are rare, but we can simulate them. And we combine data from simulation and real-world data together in order to have yet another layer of robustness. But at the end of the game, the question is valid, and I think the most important thing in autonomous driving and in automated driving is a question of robustness, is a question of whether you are able not only to behave nice sometime, but to behave nice all the time.
That was excellent. I think we are almost at our time, and maybe just one question to finish. Do you consider that with RSS that driving policy is a solved problem, or are there areas that you look to for the future, for future development?
I think that saying that a problem is solved is very dangerous. One of the top managers of Google 10 years ago said that computer vision is a solved problem, which is of course not. I think that we can improve things all the time. There is a second question. I think that there is a lot of work, and there will be a lot of work in the coming 10 years at least. The question is, when will we be good enough so that we will feel, and the public will feel through the regulators, that the situation, the driving policy is good enough, is human-like enough, is safe enough in order to take the driver out of the loop. This is, I think, the real question. I don't know when it will happen, but in terms of improving, I think at least 10 years there is more and more and more things to improve in the driving experience. And while I think that we can be ready very soon to driverless cars, I think that the driverless cars can improve much more in the coming 10 years.
Fantastic. Thanks once again for your time, and thanks to you and all your colleagues at Mobileye for the work you do with us. We're incredibly proud of what we just put into production in the form of Blue Cruise, and Mobileye is center to a lot of the functionality that's there. So we're really grateful for the partnership, and it was, I think, fantastic for this team to have somebody who has contributed so much to the field of automated driving come and share their time with us. So really appreciate that. Thank you so much.
Thank you.